distribution. And usually this exponential distribution is very closely linked with Poisson distribution. So the hint you will get in any question like X follows an exponential distribution is number one, it will be time. It will be time. Time, a continuous random variable. So in this chapter, we are talking about all continuous random variables. Two distributions that we will discuss, they are about the time until the happening of an event, time until the next success. So exponential is one of them. How it is very closely related to Poisson distribution. Poisson distribution was the number of successes in a specific time. So I made a timeline last time for you. This is the timeline each hour, and you're talking about number of calls per hour in a call center. So suppose this is the timeline of the call center. And in this call center, if you are interested in number of calls per hour, that's Poisson. If you are interested in time until next call, that's exponential. And the trick here is that in question, most of the questions I see in exercise, they will say that the number of calls per hour follow a Poisson process. And they will ask a question about find the probability of having next call within 2 minutes, within 3 minutes. So they will ask a question about time until next call, but give you the information about average number of calls per hour. So they will use the word Poisson process either, or they will use the word exponential distribution. Mostly Poisson process. Mostly they will use the word Poisson process. So this is an indication that, of course, the question will not ask you about Poisson distribution. This exam, we will not ask you about X because it's done. Poisson distribution is no more in the syllabus of this major exam. So wherever you see if any question has Poisson process, it's about exponential distribution, always about exponential distribution, or we will use straight away the word exponential distribution for the variable. Again, these questions of time until next success, they can be solved with both Poisson and exponential. Because the syllabus is not overlapping, I will not show you in the class, but those who are interested how we can solve the exponential question using Poisson, I can show you in the office hours. You can come to me. I will show you how a question of time until next success can be solved using number of successes per unit or per hour. So this is the probability mass function. I would say probability density function now for a continuous variable. This is the probability density function of an exponential random variable. This will be given to you in formula sheet. The only thing you need to identify two things. Number one, from the question, you need to recognize that the question is about exponential distribution, number one. Once you are sure that the question is about exponential distribution, there is only one parameter of exponential distribution, which is lambda. It is the same lambda that we used in Poisson distribution, average number of successes per unit, exactly the same lambda. So the second thing you need to identify from the question is what is this lambda? Once you have exponential distribution and lambda, again, it is just plug in. Just plug in. You just have to plug in the values in the PDF or CDF or mean or variance to get the answers. It is only plug in. One of the things that we will discuss additional in this one is a property of exponential distribution, which I will come to that one at the end of this slide. So let us formally define. An exponential distribution models the waiting time between the events, waiting time until next success in a Poisson process. The process is a Poisson process. By Poisson process, we mean that the event occurrence has a constant rate lambda. That means the average number of events per whatever unit is constant. The waiting time PDF is this one given to you in the formula sheet. The CDF is given to you in the formula sheet. Now for four special distributions that we will discuss in this chapter, exponential, Weibull, normal, and log normal, we do not want you or expect you to integrate. For any probability question, you can use this guy without integrating. You don't need to integrate. For example, if I ask you to find the probability of x less than 4, what is that? Capital F of 4. Just plug in the value. No need to integrate. This is the integrated version of this one. For the next Weibull distribution, again, we will give you both. You don't need to integrate. If I ask you to find the probability between 2 and 4, what is that? F of 4 minus F of 2. This capital. So for special distributions, remember the integration is not easy. For the next Weibull distribution, the integration will be very tough. So for any probability question, we will be recommending you to use capital F. For less than probability, directly capital F. For greater than probability, complement rule, 1 minus capital F. For in between probability, F of upper value minus F of lower value. So all the probabilities can be found through capital F. Then the mean variance expressions are given to you. Sometimes we give you lambda directly. Sometimes we tell you that the mean is 10. So what is lambda? 1 over mean. Mean is 1 over lambda. Lambda is 1 over mean. So sometimes we'll give you the information about mean indirectly by giving you the, instead of lambda, we'll give you the mean. So you can find lambda from there. One of the properties of exponential distribution is that it does not have a memory. It's memoryless. What do we mean by memoryless? Here is the timeline, for example. Here is the timeline, and I tell you that I will start from the beginning. Here. And from the beginning, I want you to find the probability that y is less than 1. This is the probability that the next call will come within 1 hour, right? How will you find it? F of 1. Just plug in 1 into the CDF of exponential distribution. If I tell you that I am here and there was no call in the first 2 hours, it doesn't matter. In continuous random variable, equal or not equal does not matter, because at specific points, the probability is 0. Now, if I tell you that there was no call in the first 2 hours, what is the probability that there will be a call in the next hour? This means I'm asking you that y is greater than 2. What is the probability y will be less than 3? In total. In total. I'm telling you that from beginning till 2 hours, there was no call. Now find the probability that there will be a call before 3rd hour. This is the called memoryless property. It has no memory. This is simply the same as the one that you found before. Exactly the same. You don't need to go through the conditional probability formula. Even if you go through the conditional, which I will show you in one of the questions, even if you go through the conditional formula, you will get the same. So mathematically, it can be proved that for exponential distribution, if I tell you that there was no event in first t hours, and then ask you to find the probability that either it is less than or greater than, this can be both signs, t plus s, it's simply corresponding to s, no memory. The previous memory can be easily washed. So we will use this property in one of the questions. In the same question, I will show you finding this probability through the definition of conditional probability without using the memoryless property, and I will show you, you will get the same answer. But in exam, do not waste your time in doing it with both ways. Do it with the memoryless property. Let us move on to this example. In this example, they say in a large corporate computer network, users, they log on to the system. This can be modeled as a Python process with the mean of 25 logons per hour. Lambda is how much? Is it the average number of logins per hour or average time till next login? It's average number of, so that's lambda. If I give you similarly the mean time until next log on, I'm giving you expected value of x of exponential, which is 1 over lambda. So if I give you the expected value of Python, which is number of, that's lambda directly. If I'm giving you the expected value of exponential, that is 1 over lambda. Remember, look at the expressions in the formula sheet, they will be given to you. For Python distribution, expected value of x is lambda. For exponential, expected value of y, which is given as x in the formula sheet, it is 1 over lambda.
The expression value of this is one over 4.
This is Python. This is simply lambda given to you.
Yeah.
Mean of what is given? Read here. Is it number of logins or time until next login? If it is for the exponential, we will phrase it like this. It will be, will not give you 1 over 25, we'll give you a number. Let's say we give you 2.
When I said 25, I think of 1 over 4. So
okay, now we see that your x here is time until next log on. Okay, number one, you recognize x has an exponential distribution with lambda equals 25. Two most important things. Number one, what is the distribution of x? What is x? X is the time until next login. And what is the distribution of x? Now read the question. What is the probability that there is no login in next 6 minutes? Time until next login is more than 6 minutes, correct? No login next 6 minutes. You can also solve it with Python, by the way. No login until next 6 minutes. That means the next login is after 6 minutes, correct? This means that the time until next login is more than 6 minutes. Now, one of the tricks here is that lambda is given in what units? And the question is, so either convert the question into lambda or lambda into question. So I will convert question into lambda. 6 minutes is how many hours? (0.1). So what is probability of x greater than 0.1? 1 minus capital F of 0.1. And this will be given to you in the formula sheet for exponential distribution. Put the value of lambda, it becomes, lambda is 25 times x. Okay, and just plug in the value 0.1 in this one. So this will be e to the power minus 25 times 0.1. Any questions? 1 minus became 0. So it was 1 minus 1 plus e to the power minus 25 times something. So that became 0. Question number 2. What is the probability that there is at least one login in next 6 minutes? The time until next login is less than 6 minutes. So you have a log on before 6 minutes. So here they are asking you to find probability of x less than equal to 6. Again, for this chapter, you have to convert everything into time until next login. Although you can answer these questions in the same spirit as Python, but try to convert every question into time until next login. So here they are asking you to find the probability that the time until next login is less than 6 minutes or less than equal to 6 minutes. This is simply what? Not 1 minus. This is f of 0.1. 6 minutes is 0.1 hour. And this is 1 minus e to the power minus 25 times 0.1. So this will be 0.9179. When I upload the slides on the Blackboard, the slides will contain the solution. The ones I brought in the class, I deleted the solution. But when I upload in the Blackboard, you will see that the solution will be. Next question says, what is the probability that the waiting time is between 3 minutes and 9 minutes? Simple question. Is about what? Yes. So this is capital F of 9 minutes is 0.15 and 3 minutes is 0.05 hours. So 0.15, that will be 1 minus e to the power minus 25 times 0.15 minus 1 minus e to the power minus 25 times 0.05. And this will be 0.263. Any question from this slide? Any question from these three? Yes.
The equal 6 because an interval of 6 minutes, right?
Yes. I should write here. I converted. This is in minutes, and here I converted in hours. The question says, what is the probability that there is at least one login in first 6 minutes? That means the time until first login was less than equal to 6 minutes. Here I will use yes. It doesn't matter. Yes. In any continuous random variable, it does not matter. Here it says, given no login in the first 3 minutes. Given the time until first login is more than 3 minutes. You get it? Given there was no login in first 3 minutes, what is the probability that you will have to wait at least additional 6 minutes? X is more than equal to additional 6 minutes, 3 plus 6. Simple. It is simple more than 6. You can solve it simply using the memoryless property. So here I will first make use of this memoryless property, and I will find it to be simply probability of X more than equal to 6, which is e to the power minus 25 times 0.1, which we already found in part 1, and that is 0.0821. Now, if you want to go through the definition of conditional probability, this probability will be X more than equal to 9 given X more than 3. Apply the formula. Probability of A given B is what? Intersection divided by. Now, there is an event that X is more than 3, and there is another event that X is more than 9. Here is the timeline. Here is 0, here is, let's say, 3, and here is 9. Event 1 says that X is more than 9. This is this event. Event B says that X is more than 3. It is this event. The intersection will become yellow plus blue, green. What is the green area? Greater than 3. The second event itself is the common area. So this will be probability of X greater than 3. No, greater than 9. Over greater than 3. So this will be 1 greater than, not 1 minus. This is e to the power minus 25 times 0.15 over e to the power minus 25 times 0.05. And if you solve it, it should be exactly 0.0821. Exactly 0.0821. Even through the conditional probability, if you don't want to use the memoryless property of exponential distribution, you do it through conditional, and it will give you the same answer. Compute the mean waiting time and the standard deviation of waiting time. Over 25 is 0.04, not 0. Yeah, 0.04. Units. 25 is minutes or hours? 25 per hour, so this will be hours. Or to convert it into minutes, this is 2.4 minutes. What is the standard deviation of X? The formula is given to you. The variance is 1 over lambda square. Standard deviation will be the same. 2.4 minutes or 0.04 hours. This is tricky now. Determine the median. How do you determine the median? For any continuous random variable, any continuous random variable. If you denote median, let's say by M. So to find the median, we need to solve this equation. F of median equals 0.5. Why 0.5? Because it's median. If it is Q1, this will be 0.25. If it is 90th percentile, this will be 0.9. So what is capital F of M? We are given the formula that capital F of X is 1 minus e to the power minus lambda x. This is given in the formula sheet again. So capital F of M is 1 minus e to the power minus 25 times M. And this is equal to 0.5. Can we solve this equation? One equation, one unknown, simple solution. Take e to the power on the right side, 0.5 to the left side. This will make e to the power minus 25 m also equal to 0.5. Take natural log on both sides. Minus 25 m is natural log of 0.5. And m is natural log of 0.5 over minus 25. A small question for you to think at this point. This is the negative value, right? Minus 1 over 25 times log of something, correct? But the domain of X is positive. It's the waiting time. Can the waiting time be negative?
Then 0.5 is negative.
Then 0.5 is negative value, so this is a positive value. Remember, this is not a negative value. A variable which is strictly positive, its median cannot be negative. The variable is waiting time, strictly positive. So how can its median be negative? Median is the central value of the variable. So it cannot be negative. It will be positive, and it is positive. And the value is 0.0277. What was the mean? 0.04 up there, here. And what is the median? Positively skewed or negatively skewed? Major one.
Negatively skewed.
Mean is greater, median is less. Positively skewed. So if you see the exponential distribution, it is something like this, positively skewed. The first thing will be mod, then it will be median, then it will be mean. And the opposite for negatively skewed distribution. So exponential is a positively skewed distribution. What is the value of the waiting time below which 90% of the waiting times fall? What is this? What is the value of X below which 90% of the values of X fall? 90th percentile. So we are supposed to find again, reading the question and writing this that P90 is required is 80% of the solution. 80% of the solution. Now to find 90th percentile, it's just implementation. You need to solve what? Capital F of P90 equals 0.9. So 1 minus e to the power minus 25 times, let me call it A, equals 0.9. Solve for A. So this A will be natural log of 0.1 over, I think, minus 25, is it? This will go there, that will come here, 0.1, then ln of 0.1 divided both sides by yes. And this will be 0.0921. 0.0921 hours. And that's it. This was exponential distribution. Each and everything that you can expect from a question about exponential distribution, I tried to cover in all these examples. Any question? Yes.
Let's find the percentile of 100.
100 percentile for exponential, because the upper bound is infinity, you cannot. You can find 99.999999%, but not 100, because the upper bound is infinity. There is no upper bound. Any questions before I move on to the next distribution? Okay, now the drawback of exponential distribution is that we are assuming that the rate of occurrence is constant throughout. And this is usually not the case with many real life engineering problems. Here you are assuming that what is the rate at which the people were logging in the first hour? It was 25 people per hour, right? What about second hour? 25 people per hour. Yes. What about third hour? 25 people. Usually it is not the case. When you are sitting in the office, people are enthusiastic in the morning. The rate of login is higher in the morning. Then as you go along in the evening, the rate of login goes down, right? So this rate is usually changing. Exponential distribution does not have the capacity to accommodate the rate of logins changing through the time, because it has only one parameter and it has a fixed rate of occurrence. Lambda is fixed. So it does not have the capacity to model those real life engineering problems where the rate of occurrence is changing, either increasing or decreasing. Yes, that's what we do. And when not as a function of time, we introduce another parameter, beta. And this beta controls how lambda is changing over time. So if beta is 1 here, that means you go back to the exponential. So this Weibull, you can think of this Weibull distribution as an extension of exponential distribution. So exponential becomes a special case of this Weibull when beta is 1. And even in the PDF, if you see, when I put beta equals 1, what is beta 1 minus 1? 0. This is 1. 1 over delta e to the power minus 1 over delta. So lambda becomes 1 over delta. So it becomes same as exponential. This distribution has an additional parameter beta, and this beta does what? It controls how the occurrence rate is changing. If beta is more than 1, that means over time the occurrence rate is increasing. Number of people logging in per hour is increasing. If beta is less than 1, that means over time it is decreasing. The number of people logging in per hour is decreasing over time. So it gives you added benefit of another new parameter that controls the number of successes per unit. Increasing or decreasing, it can control. If you don't want to increase or decrease, beta 1 will take you back to the constant rate of occurrence. So here are the key points. Exponential distribution models the waiting time when the event occurrence is fixed. The rate of event occurrence is fixed, whereas the Weibull distribution generalizes this by introducing another parameter beta, which allows the occurrence rate to vary over time, either increase over time or decrease over time. So if beta is more than 1, occurrence rate is increasing over time. If beta is less than 1, occurrence rate is decreasing over time. When beta is exactly equal to 1, the Weibull distribution reduces to exponential distribution, making exponential as a special case of Weibull. This is more versatile than exponential. And the key here is that this is also used to model the waiting time till next success, till next event occurrence. But here, now the event occurrence will not be constant. The good thing is that we will not test the concept of recognizing that a variable follows Weibull. If a question is from Weibull, the question will mention Weibull. It will not link you through the Python. For exponential, it might link you through Python. But for Weibull, if there is a question from Weibull, it will use the word Weibull. So don't worry about trying to read the question. The question is about waiting time till next success and the occurrence rate is changing. So now it is Weibull. No. If there is a question from Weibull in exam, the question will clearly use the word Weibull. So the question will tell you that X is Weibull here. You are just supposed to do the implementation. For the implementation, here are the formulas. Here is all the trick in the last line of this slide. What is the trick? The trick is that we might give you the two parameters of Weibull distribution and ask you to find the mean and variance. And as you can see, the mean and variance is a function of gamma function. Are you all aware of gamma function? Many of you are not aware of gamma function, so I will cover how do we find the gamma function in the next slide. This notation that I used at many places, this is called a gamma function. This guy is a gamma function. This is gamma of 1 plus 2 over beta. This is gamma of 1 plus 1 over beta, and so on. So I will train you how to find the gamma function on calculate. Because at the end of the day, in exam, we will not give you the access to the software. You have to calculate the gamma functions on the calculator. So I will tell you what cases you expect in exam and how to find the gamma function of those cases. Again, let me repeat, for Weibull distribution, the question will clearly mention that X follows a Weibull distribution, and it will either ask you for greater than probability, direct plug into which function? For probability, direct plug into which function? This function. If the question asks you for less than probability, direct plug into this function. If the question asks you for in between probability, direct plug into this function. If the question asks you for a percentile, solve the equation for this function. If the question asks you for the mean or variance, put the values of beta and delta, the two parameters of Weibull, into these functions. And how to solve these functions? Let's go to the next slide now. Okay, this is the example, and as you can clearly see that the example will use the word Weibull distribution. Clearly, it will use the word Weibull distribution. So the example says that assume that the lifetime X of a bearing in a mechanical shaft follows Weibull distribution with parameters beta equals half and delta equals 5,000. Direct substitution, but in this case, direct substitution is easy. In next cases, it will not be easy. In many cases, it will not be easy. So we gave you the mean and variance expression. The mean and variance expression are in the formula sheet. You have to substitute these expressions into mean and variance. So let us first substitute, and then I will tell you where the things can go wrong. So for the mean, this will be given to you in the formula sheet. Delta times gamma of 1 plus 1 over beta. If you plug in, what is the delta given to you? 5,000. And then gamma of 1 plus, what is beta given to you? 1 plus 1 by 2 is what? 2, right? 1 over half is 2. And this is 5,000 times gamma of 3. Now, this is situation number 1 when you have to solve the gamma of an integer. If you have to solve gamma of an integer, read this line. What does it say? Gamma of any integer is the same integer minus 1 factorial. So 3 gamma is 2 factorial. 7 gamma is 6 factorial. 4 gamma is 3 factorial. Are you all aware of factorial? Good. So in this case, 3 gamma is what? 2 factorial. So this is 5,000 times 2 factorial. 10,000, right? Let's move to the standard deviation. For the standard deviation, this formula is given to you. 1 delta square gamma of 1 plus 2 over beta minus gamma of 1 plus 1 over beta whole square. This is given to you. Just again, the plug-in. When you plug in, what is delta square? 5,000 square gamma of 1 plus 2 over half. What is 2 over half? 4, 4 plus 1, 5, plus or minus? Minus 1 plus 1 over beta was 3, right? 3 gamma whole square, then whole square root. Again, the two gammas you got are integers, so no problem. 5 gamma is what? 4 factorial, 24, and 3 gamma is 2 factorial, which is 2. 2 times 2 is 4. So this is again easy. I think I missed something. I missed delta here, is it? I missed delta here. So this will be something. Now imagine a situation, I give you a question where beta is 2. Beta is 2. Now what will be the mean? So this is 5,000 multiplied by gamma of 3 over 2. Now for any question where you need to find the gamma of an integer divided by 2, and the integer is not an even integer, it's an odd integer. 3 is an odd integer, right? This will not turn out to be a whole number, correct? So if there is any question where you are supposed to solve a gamma function of an even integer divided by 2, you will use this identity, n divided by 2 gamma for all n even integer. This is equal to n by 2 minus 1 into n by 2 minus 1 gamma. And you can sequentially keep opening the gamma function every time. As an example, if I ask you to find a 3 by 2 gamma, 3 by 2 gamma is equal to, what is 3 by 2 minus 1? So it is 1 over 2 times 1 over 2 gamma. And when you reach to a point where you have 1 over 2 gamma, you will use this result. 1 over 2 gamma is square root of pi. Let me give you another example. I ask you to find 7 over 2 gamma. What is 7 over 2 minus 1? 5 over 2 times gamma of 5 over 2. Then again open 5 over 2 gamma. What is 5 over 2 gamma? 3 over 2 times gamma of 3 over 2. Then again open 3 over 2 gamma. What is 3 over 2 gamma? 1 over 2 times gamma of 1 over 2. Keep doing this until you reach 1 over 2 gamma. And finally, 1 over 2 gamma is square root of pi. So this will be 5 over 2, 3 over 2, 1 over 2, square root of pi. We will not give you any question where the expectation will turn out to be either gamma of a whole integer or gamma of a whole integer divided by 2. We will not give you a question for gamma of 1 over 3. That cannot be solved on a calculator. So if there is a question, even the second case I'm giving you here for something divided by 2, very rarely it comes in exam. But still, I'm telling you how to do this one. If there is a question asking you for gamma of 3 over 2, you should know. 1 over 3, no need to know. Yes. I checked last night for basic calculator, no. For advanced calculators, yes. But according to the syllabus, you are not allowed to bring the advanced calculators. You need to do this, or for the integer, simply factorial. Okay. I'll give you 2 minutes and I will finish this one. What is the probability that the bearing lasts at least 6,000? At least 6,000. The time until next failure is at least 6,000. Greater than 6,000. Again, this is what? 1 minus f of 6,000. F of x is given to you in the formula sheet. What is the probability that the bearing fails before 4,000? Before 4,000. This is simply capital F of 4,000. Determine the median. solve this equation. This is the tricky question. If you select 5 bearings, what is the probability that all of them will last for more than 6,000? What was the probability that one bearing lasts for more than 6,000? You found it in part A. Part A, you said that probability here. One bearing lasts for more than 6,000 hours. You found this probability to be 0.3347. Now, last question is saying that you have 5 bearings, not one bearing. 5 bearings. What is the probability all of them will last for more than 6,000 hours? Raised to the power 5. This is actually the probability that first bearing lasts for more than 6,000, and second bearing also lasts for more than 6,000, and third also lasts for more than 6,000, and fourth also, and fifth also. And because the question is saying they are operating independently, so when two events are or more than two events are independent, and becomes what? Multiplication. So it is 0.3347 multiplied by 0.3347 multiplied by 0.3347 multiplied by, so this will be or you can also solve it from binomial. N is 5, P is 0.3347, and probability of Y equals 5. So this is 5 combination 5, P to the power 5, Q to the power 5 minus 5. Anyways, you can solve it. So this is end of Weibull distribution. Again, I want you to complete this example yourself. I will post the slides at the end of this chapter. The slides, of course, will contain the solution. And next class, I will start the all-important normal distribution. This second major exam, at least 30% of exam comes from the normal distribution. At least 30% of the exam comes from normal distribution. So come prepared for the next class and pay attention.